CCM-DCM boundary condition. So, we know that I load should be what? Delta L by 2, and what is delta IL? Let us write in terms of V out only, over L, correct. So, what is 1 minus D? 1 minus D is I load over L into, sorry, I load over TSW into L over V out, correct. And what is V out? What is I load in terms of RL, if I want to write? Which means 1 minus D equal to, so V out will get cancelled out. So, you will get, there was 2 factor also. Yeah. Correct. Or D naught equal to 2L over, which means 1 minus D should be what? This is the boundary condition basically, which is depending on what? Switching frequency, your load and inductor. So, it should be less than or greater than this D naught. Huh? Yeah, greater than for CCM. For DCM, it should be less than this. Okay. So, if you are increasing the load current, decreasing the load current for the same switching frequency. So, what exactly will happen actually? You will be outside the boundary, above the boundary, and as you reduce, you hit this point. So, what is happening actually, if you see, you do not allow this negative current, which means your off time has to be reduced to keep it in the CCM. Okay. So, this is your boundary condition, and we will call it K, which is critical factor, let us say, and this is a fixed based on your inductor, your switching frequency and your load current. So, we will use this equation later. Let us mark it number 1, and now come here. If this is your PWM waveform, this is T on and this is T off. Let us say my inductor current is rising, and I know that if I am operating in the DCM, the current has to go to 0 before you hit the next clock cycle. So, which means before your T off gets over, current should reach to 0 and it will remain flat here 0. So, this is your 0 amp point. Then again it will rise and do the same thing. inductor current. Let's plot the VSW. How will it look like? So, when PWM is high, VSW should be okay, and this will be VDD and this will be 0. What would happen here in this case? When PWM goes low, what should be the VSW? Your bottom FET is turning on, it should go low. What would happen here? It will remain low or go somewhere else when current goes to 0. Where will it go? V out, because that's a high impedance. That is how waveform looks like. So, this T on remains T on. If I call this as T of 1 and this as T of 2. So, what is the average? What should be the average voltage across inductor? VL of, what is the condition for regulation? What should be the average voltage? 0, So, from this waveform, we can find the average. So, what is the average? So, during T on, what is the voltage across the inductor? VDD minus V out into T on plus during T of 1. Okay, so plus minus V out T of 1, and what is the voltage during T of 2? 0, because both nodes are at the same voltage. And divide by one over TSW. That is your average voltage. So, L and TSW will go away, that is common to both the voltages during T on and T of 1. So, leftover will be VDD minus V out into T on minus V out T of 1. So, what is T on plus T of 1 from this? VDD by and what else? T on, correct. So, this was the one condition. What is the second condition for regulation? So, this was based on voltage. What is the condition for based on current? Average inductor current should be same as load current. So let's which means we need to find the area under this triangle. So IL average what is the area? Half. So this guy is T on T of 1 T of 2 what is the height of this inductor? VDD minus V out over L into T on or D times TSW. And during T of 2 the current is 0. So average current will be nothing but area under this triangle equal to I load. From second equation T on plus T of 1, how much is that? VDD over V out into T on. So we need to substitute this. So I load equal to half of VDD over V out T on and okay, can I write VDD and what is load? Let's write. What is I load? V out over RL. So this guy will go away. Half of VDD V out. So now we have two T ons, huh? T on square. Sorry? Which one?
Divided by T.
Which last term?
So the total divided by total. I load the area by T step.
Oh, that one divided by. Oh, sorry. Yeah. So wait. Let's write here. Okay. Correct. Fine. So now if you remember this guy, this equation you should remember actually. We will use this. Let's first move the things and then I'll put it here. for now. So TSW 2 and L can be moved on the other side. And what is T on?
D times.
Okay, so over TSW into half into VDD over V out D times TSW again D times TSW. So 1 will go away. So what you have D square. So VDD over V out into VDD minus 1 equal to D square equal to twice of L over RL TSW. Correct? And we know this is nothing but equal to what? K? You have to simplify this. VDD square, VDD over V out square, multiply these two, minus VDD over V out minus, so I will move this D square in the denominator on the right hand side and shift everything on the left hand side. So it will become K over D square equal to 0. So it is nothing but VDD over V out equal to x. So x square plus bx plus c. So what will be the roots? X is equal to minus b. Minus b is nothing but 1 plus minus square root b square minus 4ac. So c is negative. So this becomes plus 4k over d square. Correct? Which means VDD or V out over VDD is 1 over 1 plus minus square root so we are we are deriving this condition for a buck converter. For buck converter, V out over VDD should be less than 1. So if this becomes 1 minus this term, then this will be more than 1. So the negative term is not valid, which means V out over VDD can't be 1 over 1 minus there was 2 terms, 2, yeah, there should be 2, divided by 2. Okay. One plus 4k K you already know is this. So if RL tends to infinity, then what would happen to K? 0. So what will happen to V out over VDD? 1. This implies in DCM under no load condition your output will go to V in, it will saturate.